Here is a magazine that I enjoy reading. This is the current issue, April 2020. The timing of this magazine couldn't be better because it talks about our galaxy. And our word problem today, we're going to go out into space. What we see here is a picture of our galaxy, the Milky Way. It's not an actual picture of the Milky Way, it's an artist's rendition based on scientific data of what our Milky Way would look like. Looking inside, and this is the current idea of what our Milky Way looks like with 4 spiral arms. Again, this is an artist's rendition based on the scientific data that has been gathered. And we are located somewhere here within the Milky Way galaxy. Our little solar system with the sun at the center is about here. And today we're going to talk about a supergiant star called Betelgeuse. And Betelgeuse is in our galaxy, somewhere in here. The thing about physics, with your imagination, a little bit of mathematics, we can go anywhere in the universe. Let's have a look at what our word problem today. The supergiant star Betelgeuse has a surface temperature of about 2900 K. Whenever I see this word, I'm always reminded of the movie Beetlejuice. Here it is. I like this movie, and I like to say the name Beetlejuice. So I'm going to take some literary freedom and simply pronounce this Beetlejuice. So a supergiant star Betelgeuse has a surface temperature of about 2900 K and emits radiant power of approximately 4 times 10 to the 30 watts. Assuming that Betelgeuse is a perfect emitter and spherical, find its radius. Equation we're going to use is the radiant heat equation. Q is equal to E sigma temperature to the power of 4 A T. Within the problem, it says that Betelgeuse emits radiant energy into space at a rate of 4 times 10 to the power 30 watts. This is known as radiant power, or rate of energy being emitted out. And I talked about this word rate of energy before, and rate is something divided by time. That something divided by time is in joules per second. Joules per second is also a watt. So we can also use the word radiant power. Looking at our equation, changing this into rate, E sigma temperature to the power of 4 area. This term right here, Q over T, that's a joule per second. A joule per second is also known as a watt, and watt is a unit of power. So this term can be called radiant power. In a previous video, I mentioned that Q over T is also known as rate of radiant energy. Betelgeuse being a star, it has energy, and it is emitting this energy into space. Radiant power, or rate of radiant energy, being emitted into space. Now that we understand the actual equation, let's have a look at what is given. E, it says here, assuming that Betelgeuse is a perfect emitter, emissivity is equal to 1. E is emissivity. When you see the term perfect emitter or black body, a black body emitter, also known as a perfect emitter, we're going to use the value of 1 for E. I will leave this word black body for you to research. There's a lot of history behind this one, but I don't have the time for this video to discuss black body, so we'll simply use anything where you see perfect emitter or the word black body, use E equals 1. And remember, E has value somewhere between 0 and 1. This one here being the perfect emitter or black body. In our equation, we have sigma next. Sigma is equal to 5.67 times 10 to the power of minus 8 joules per seconds meter squared Kelvin to the 4. And we have temperature. Temperature was measured by scientists at 2900 Kelvin on the surface of Betelgeuse. Over here is Q over T, or radiant power. And that's given to us as 5 times 10 to the power of 30 watts or joules per second. And assuming that Betelgeuse is spherical, and it has we need to find its radius. Now we'll write down what we need to find. Radius, we don't know. And the surface area of a sphere, that's what this represents, surface area. Surface area of a sphere, assuming that this is spherical and planets and stars are spherical. Surface area of a sphere is equal to 4 pi r squared. So area is equal to 4 pi r squared. Surface area is equal to 4 pi r squared. I'm going to substitute the right-hand side of surface area into here. And that changes our equation. That looks like this. Radiant power is equal to E sigma temperature to the power of 4 pi r squared. Replacing area with the right-hand side of surface area. And here then is the radius that we are seeking. It's hidden within area. We have everything we need right now. Just a matter of taking all these values, and I'm going to bring the units along and rewrite the whole equation here. Radiant power it's watts, but I'm going to use the words or the terms joule per second. Is equal to E for perfect black body is 1, and sigma Kelvin to the 4 times the temperature to the power of 4. The temperature was 2900 K Kelvin. Everything to the power of 4. And then multiply everything by 4 pi r squared. Effectively, the physics is done at this point. All that's left now is algebra in order to solve for r. First thing we need to do is remove these brackets and bring the 4 down. So 4 operates on the temperature 2900 as well as the units. So rewriting this, removing these brackets. And 2900 to the power of 4 Kelvin to the power of 4. Everything times 4 pi r squared. I'm going to go over to another page and complete the algebra like this. Everything is multiplied, and I need to isolate r squared. going to begin by bringing the 1 to the left-hand side, 5.67 to the left-hand side, of 2900 to the left-hand side, and leave this on the right. Everything divided by 1, divided by the constant, and divided by the temperature. And that's all equal to 4 pi r squared. Looking at the units on the left-hand side, emissivity is a dimensionless number, no units. Kelvin to the 4 cancel out. That's in the numerator, and there's a denominator. Joules per second, joules per second, joules per second, joules per second, leaving us with meters squared. And that's a good thing because radius is in terms of meters, and radius squared will be meters squared. Rewriting this, everything divided by -8, and it has the units of meters squared left over, times 2900 to the power of 4. What we need to do now is take 4 pi and bring it to the left-hand side. So if I divide both sides by 4 pi, it effectively brings it to the left-hand side. Is equal to r squared. Meters squared, when this is done, is going to come to the numerator. Looking at all these numbers now, and putting this in a calculator, the number will be 7.9373416 times 10 to the power of 22. And the meters squared, and I showed that in the previous video, it's in the denominator here. It's going to be to the numerator. Meters squared is equal to r squared. Careful when you use the calculator. Press equal sign often. Taking the square root of both sides, and I'll take the square root of everything here, including the units, and the square root of the right-hand side. Placing this in the calculator, doing the square root, that number is 10 to the power 11 meters is equal to r. I'm just simply going to reduce this to 3 significant figures. Just for ease, 2.82 times 10 to the power of 11 meters is equal to the radius of Betelgeuse. How big is that? Well, if I look at some values of our planets and the radiuses that when they orbit our sun, here are some terms of our planets and their orbit radius around our sun. Betelgeuse would occupy a space about this large, just over. Here's our sun. Next to it is Mercury. Next to that one comes Venus. And then comes Earth. And next one after that one is Mars. And Mars, according to the literature that I just showed you earlier, has an orbit radius of 2.28 times 10 to the power of 11 meters. And the planet after Mars is Jupiter. and its radius orbit from the sun is 7.78 times 10 to the power of 11 meters. And we calculated Betelgeuse have a radius of 2.82, and will lie in here. At 2.82 times 10 to the power 11 meters. That would be the size of Betelgeuse, completely encompassing our little Earth. Supergiant indeed.